Alright, in this video we'll talk about writing Lewis structures for polyatomic ions, and then we'll address some exceptions which are always prevalent, and then we will take a look at resonance structures. So first, polyatomic ions. We are going to write these Lewis structures the same way that we do for other covalent compounds, but we just have to pay close attention to the number of electrons. And so whenever we have a polyatomic, we have a charge, and so if we have a positive charge, then we will subtract an electron from the total number, and if we have a negative charge, then we'll add electrons for each of the negative charges. The other things for polyatomic ions is that we'll show the final structure within brackets, and we'll write the charge of the ion in the upper right-hand corner. We start by writing the skeletal structure, nitrogen in the center, and then the hydrogens as our terminal atoms. We'll calculate the total number of electrons. So we have 5 for nitrogen. We have 1 for hydrogen, but we have 4 of them, so we have 4 from the hydrogens. We will subtract 1 electron because of the positive charge for a total of 8 electrons. We'll put our electrons between our atoms, and this will give us 8 of 8 electrons. And so our final structures will be this, with our dots for our electrons. We'll use the brackets with the positive charge, or we can draw the lines to demonstrate our pairs of electrons. So let's go ahead and do another example together. So we'll do an example for the cyanide ion. So we'll draw our skeletal structure, which will just be C and N. We will do our valence electrons, so we have 4 from carbon, plus 5 from nitrogen, and then we have a negative charge, so we will add 1 additional electron for the negative charge, so we'll have 10 total electrons. We'll go ahead and place our pairs of electrons, and so we have 2 electrons here, and then we'll go ahead and start with nitrogen. So that's 6, 7, 8, 9, 10. Okay? Now, we're going to go ahead and make sure that it has an octet. In this case, you can see that it's not. Nitrogen is fine, but carbon still needs 2 more pairs. So we'll take 2 pairs from nitrogen and move them to the middle. So our structure will be this. We'll have 3 pairs of electrons being shared. If we count up, we still have our 10 electrons, so we can either draw like this with a negative, or we can draw like this with our triple bond and our negative on the outside. Let's go ahead and practice. You can pause and then check back for the answers as well. So for hydroxide, we'll have O and H. Oxygen has 6 valence electrons. Hydrogen has 1. And then we'll add 1 for the negative charge. So we'll have 8 electrons. So go ahead and do 2, 3, 4, 5, 6, 7, 8. So we can draw like this with a negative, or it can be oxygen with the 3 lone pairs, the line for the bond, and hydrogen, put a bracket with a negative. For hypochlorite, we have 7 valence electrons from the chlorine, plus 6 valence electrons for the oxygen, plus 1 additional for the charge, and so we'll have a total of 14 electrons. Our skeletal structure, since we just have 2, would be the chlorine and the oxygen. We'll go ahead and put in our electrons. 6, 7, 8, 9, 10, 11, 12, 13, 14. So we can draw it like this with our negative. We've used all of our electrons and everything's happy. Or we can draw like this with our negative charge. Finally, you can go ahead and draw Lewis structures for each of these as practice, and then answer which 2 species have the same number of lone electron pairs in their Lewis structures. So you can pause and practice. The answer is on the next slide. So the ones that have the same number of lone pairs would be our NH3, which is this one. It has 1 lone pair, and then our hydronium, which is H3O+, which also has 1 lone pair. So let's take a look at exceptions to the octet rule. As you know, in chemistry, there's always a few exceptions. So sometimes the Lewis model just doesn't quite work, or you're unable to make good models because of an odd number of electrons. So in that case, you just have to write the best structure that you can. For example, In nitrogen monoxide, we have 11 total electrons, and so you would have one electron that doesn't have a pair, and in this case you just have to make it as best you can. We'll leave that lone pair with nitrogen, and the structure is shown below. Another exception are electron deficits, meaning that it doesn't need 8 to have a stable octet. So an example of that would be boron. Boron forms compounds with 6 electrons in the outer shell rather than 8, and so those Lewis structures are drawn below, but boron is an example of something that can form with less than that 8 for the stable octet. There are also elements that have an expanded octet. Expanded octets will form with elements in period 3 and beyond, and this is because of the D subshell, which expands what we normally see for 8 electrons. Common ones that are going to have expanded octets are sulfur, which can have 12 pairs, so it can have 6 bonds, phosphorus, which can have 5. Xenon is also another example. I believe it also can form 6 bonds around that central atom. Another difference, or something else that happens for Lewis structures, is that we can have resonance structures, which mean that they are equivalent Lewis structures for the same molecule. This happens whenever there can be structures written in more than one way, so there might be 2 different types of bonds, meaning that there's a single bond and a double bond between 2 of the same elements. Whenever we write the skeletal structure for these, we're going to follow the same rules. We're just going to maybe have to add one additional thing. So for sulfur dioxide, again, we're going to, this will just show steps 3 and 4, but we've drawn our skeletal structure, we've counted up our number of electrons, which is going to be 18 electrons, and then we're distributing. So we distribute, and we finally distribute to the central atom, and what we see here is that if we've done this, then we have 8, which is good for oxygen, 8, which is good for this oxygen, but only 6 electrons for this sulfur. And so we need to move electrons to the middle, but we can move it from either oxygen. So we can move it from this oxygen, which is what's shown below, or we can move it from the other one. So since the central atom doesn't have an octet, and we move those in, this is what creates a resonance structure. So we can have oxygen double bonded as shown, or we could have the oxygen on the other side double bonded like this. And so these structures are resonance structures. In actuality, the bonds are going to be really equivalent if we measure them in nature, and that the length will actually be an intermediate between a double and a single bond. With resonance structures, again, we're just going to represent the molecule by showing and drawing both structures. So we'll write a double arrow between the 2 structures, and it's just a different position between the bonds, not really the atoms themselves. And again, whenever we look at this in nature, the bonds are actually equivalent on both sides, and they'd be more of an intermediate between that single and double bond length. Let's go ahead and do some practice for these. So we will draw the Lewis structure for the nitrate ion. So we'll go ahead and start with the skeletal structure. So nitrogen in the middle, it's the least electronegative, plus it helps to make it symmetrical. We'll count up our electrons. So we have 5 from nitrogen, we have 3 times 6 for the oxygens, and then we'll add 1 additional for the charge. And so with this, we have 24 total electrons. We're going to go ahead and distribute our electrons between the atoms first, and then to our terminal, so that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that accounts for all of our electrons. And the problem here is that whenever we look at our octets, nitrogen only has 6, and so we see nitrogen has 6 electrons here, which means that we need to pull in our electrons from one of the oxygen atoms, but we have options. So we can pull it in from the oxygen on the right, and we put our brackets around it. We can pull it in from the oxygen on the left. We'll draw our pairs to be the most correct. Okay, and then our final resonance structure would be with the top oxygen, and so I'll draw it up here since I'm out of space. So we would have nitrogen double bonded to the top oxygen, and then single bonded to the oxygens on the side. Again, in actuality, this would be kind of rotating quickly, and all of these bonds would be kind of an equivalent length, somewhere between a single and a double bond.